Okay, welcome to Computer and Network Security. Our lecture today is going to be on types of security attacks and services. So, just a question to get you to start thinking about different types of security attacks. Where there are a lot of different terms for attacks. You probably have heard about Trojans and viruses and worms and malware and adware and all kinds of different terms. So I want to start off talking about what the differences are between these. To begin, these terms are all just semantics. So there are different definitions for each one of them. It depends on who the author is for how they define each one of these terms. I've chosen to go with a paper by Karasand. I think that the author does a very good job explaining some of the differences between them. The most important thing when you're looking at characterizing malware is going to be to understand what it does, because that's how we're best going to be able to combat it. So here are just some generic definitions for Trojan horse, virus, and worm. Malware or malicious code is going to be the overarching term, and then we're going to have specific characterizations beneath that. So a Trojan is a program that performs an unknown and unwanted action for the user while posing as a legitimate program. So you may think that you're running a program and it's doing something, and you might actually even be getting the results that you want, but behind the scenes there's something else going on that you don't know. This is often one of the problems with people who complain about their computers being very slow, and they're not running anything that looks illegitimate. Oh, that's just my email program. That's a plugin that I have to my email program so that I can send emoticons. Not realizing that it's actually doing things behind the scenes and sending those same emails back to some other email server so that they're being tracked in all of the emails that they send. So it's important when you download a program that you understand exactly what it does and that it's from a legitimate and a trusted source. A lot of open source software is not that way. With the big flux that we have of smartphones, this could have been an even bigger problem, but the companies like Apple and Google decided that they were going to start regulating the programs that are run on their phones. So whenever you download a phone from like the Apple Store on your iPhone, it's already gone through a test, that Apple has tested it and made sure of exactly what the purpose is, and that there's nothing malicious, or at least that they didn't catch that there's anything malicious going on behind the scenes. When you download something from the Google Play Store, it'll pop up and say, here are the different services that are used on this. So whether it's going to be accessing the network, using the cellular data, whether it's going to be having access to your photo gallery, your pictures, and so on, it pops up so that you know at the time that you download that program and are installing it that these are the features on your phone that this application is going to be using. And then you can look at it and say, well, why does that application really need to have access to all of the pictures that I have on my phone? And you might want to think about it if that's the case. Do a little bit of searching online and find out if there's a legitimate use for it, or possibly they're trying to put something in there to have access to things that they don't actually need on your phone. So that's a Trojan horse. The second one is a virus. A virus is a self-replicating program that attaches itself to a host program and only resides on the infected host computer. The way this term actually comes from the biological term for a virus. So a virus can't live outside of a host body, and a virus on a computer isn't going to be able to live unless it is on a host computer. So one way to get rid of viruses on a network, turn the computer off that has the virus. And then that virus is not going to be on that network anymore. It's going to stay on the host computer unless it is sent or transferred to another computer, and then it will affect that one as well. The third type of malware we'll discuss is a worm. A worm is a self-replicating standalone program that replicates over network connections. Worms can get very, very difficult to fix because they are going to replicate themselves, and somehow they're going to communicate with other computers to which your computer is connected, whether this is through email, whether this is just through your internet connection, or whether it's because you're on a local area network and it just goes out and replicates to all of the other computers that are on the network. Worms are very, very bad for network administrators because they can infiltrate a network in a matter of seconds. If a computer gets a worm that's on a local area network and all of the other computers that are on that network are trusting that computer, then that worm would be able to infiltrate all of the other computers on the network in a very, very short amount of time. That then would require the network administrator to go around to every single computer or to release some kind of a fix or a program so that every user in that organization would have to run a program to get rid of the worm. As I mentioned, these definitions are just very generic, and different authors will have different definitions of the differences between a Trojan horse, a virus, and a worm, and there's a lot of different classifications of malware in addition to those three. Those are the three more common ones, which is why I chose to put them into this lecture. What's most important, though, is understanding what that piece of malware does so that we can best combat it. Different antivirus vendors, such as McAfee and Symantec, may characterize malware completely differently than other organizations do. As long as it comes from a legitimate source, chances are Symantec is going to be able to figure out what the problem is and then correct it if they know that that piece of malware exists. Okay, an outline for today's lecture. We'll go over types of security attacks, what we just did, how we classify threats, a few sample attacks where we can determine whether we think they are Trojans, worms, or viruses, and then we're going to talk about some specific topics: security in VANETS, which is vehicular ad hoc networks, MANETS, mobile ad hoc networks, and WMNs, which are wireless mesh networks. Okay, to start off, we're going to talk about passive attacks. Passive attacks just use eavesdropping or monitoring transmissions to obtain information. So a passive attack could just be that you have a router sitting on the internet and other routers are passing traffic through it, and your router's sitting there just reading all of the different data that's coming through it. There's nothing wrong with this if you own that router, or if a third-party company owns that router and other companies or organizations are routing through it, then the data eventually is making it onto your hardware. And so you just take a look at what the data is that's passed through there. If the data is not encrypted, then it's very easy for a program running on that router to just get access to the data which is coming through it. Something else that a lot of these passive attacks do is analyze the traffic. So we can figure out what type of traffic. Traffic is typically very bursty on the internet, where we will have times of the day like right when people wake up in the morning and right when people get home from work, where we have a lot more traffic on the internet. And then in the middle of the day, we have less traffic on the internet, which is kind of odd since people are at work and chances are they are using the internet, but they're not using it hopefully for the same purposes that they do of their personal reasons before they leave for work or when they get home, of watching videos on YouTube, seeing how many cats have hit penguins onto the ice today, and so on. So we can watch and see what the traffic looks like, and this will give a good indication to passive attackers to see when something is out of the ordinary. This is actually something that network administrators do with intrusion detection systems. They are able to see what their typical traffic patterns are like during the workday and at night, and then they can write a program that analyzes this, and if the traffic comes in a different order, or if it's just a little off, if something doesn't seem right, it can alert the network administrator that they may need to take a look at what is going on and see if somebody just decided that they were going to stream a Blu-ray movie to their computer while they were at work, or if maybe there is an attack going on at that point. Since the data in a passive attack is not typically altered, you're just listening to the data, reading it, and it's continuing on its way, it's typically very difficult to detect a passive attack. So what we do with passive attacks, the emphasis is usually on prevention rather than detection, because we're probably not going to be able to detect when a passive attack is occurring. What we can do is encrypt our data, which is going back and forth between us and whoever we're communicating with. What that will allow us to do is hopefully that the passive attack is not going to be able to get access to any of the data that we're transmitting. So encryption is typically the way that we prevent passive attacks, since it's nearly impossible for us to detect passive attacks. Active attacks, on the other hand, involve some kind of a modification to the data or a creation of a false data stream. There's four main active attacks that we'll discuss. The first one is masquerading. This is when one entity pretends to be a different entity. Pretty straightforward. You're on a router on a computer somewhere in the middle of a data stream, and you just are going to act as if you're somebody else, and you're going to send the data as if you're coming from another computer. This is called masquerading. A replay attack. Replay passively captures data and subsequently transmits it to produce an unauthorized effect. This one is a pretty interesting one. Let's say that you are sitting on a router in a network. Data comes through there, and you don't necessarily even need to know what the data is. It could be encrypted, and you just hold on to the data at that point. So instead of the data making it all the way to the destination right at the time that it was transmitted, you hold on to it for a little while. And then maybe a few minutes later, an hour later, however long you want, you then transmit those packets exactly the way that they were transmitted at first, even though they never reached the desired host. At that point, you may have the ability to get access to those resources. So that's a replay attack. What you also can do with a replay attack is maybe let the data go ahead and go through, and you're going to receive what the data coming back is, and you hold on to it, and then when you replay the initial transmission a second time, see if the data comes back the same way again. And you can do some pretty tricky things with that, so that would be able to produce an unauthorized effect with a replay attack. Modification of messages. This is where you change a portion of the message, delay the message, reorder the message. So you get the message and then you change something in it to see what the effect is. And if the data is coming back from the server or from whoever you're communicating with back along the same path, you might be able to see something different based on how you've modified the message. And the last one, denial of service. This inhibits the normal use of communication facilities. We'll have an entire lecture in the future of this class dedicated to denial of service, and we will also have one dedicated to a distributed denial of service. And this is where one computer or one program is denial of service, where one program or one computer is going to stop some resource from either being able to be accessed or being able to respond to requests just by different means, transmitting a lot of messages, ping of deaths, and so on. We'll talk about some different denial of service attacks in the future. And the distributed denial of service attack is even harder because that's where you have multiple computers that are all attacking one or more computers. So it makes it even harder to detect because you have so many different computers that are all doing the same thing at the same time, and it's hard for you to prevent all of them from doing something. Whereas if it's only a single computer, maybe you could just block an IP address or a MAC address from communicating, or just ignore it. But with multiple computers, you have to be careful that you're not blocking legitimate requests that are being made to that service. Okay, here's an overview of the differences between passive and active attacks. First of all, passive attack is difficult, if not impossible, to detect. They typically can be combated with encryption. As long as we're encrypting the data that's going back and forth, we probably will be able to combat a passive attack. Active attacks, on the other hand, are going to be very difficult to prevent, if we're even able to prevent them. This would require physical protection of all communication facilities and the exclusion of being able to communicate with any of the computers. So they're difficult to prevent, if not impossible to prevent. However, active attacks we are able to detect. Just being able to detect it has a deterrent effect, and hopefully this may in turn contribute to prevention. A lot of security measures are intended to be deterrents. If somebody really wants to get into a computer network, or if they really want to get into a physical facility like a house, it's not going to matter if you have a security system, they're still going to be able to get into it. A security system, if you have an alarm in your home, is acting more as a deterrent rather than preventing somebody from getting in. It's deterring them because houses that don't have security systems are going to be easier targets rather than the ones that do. This is the same idea with computer networks, that we want to try to have a deterring effect as opposed to being able to prevent, since we're probably not going to be able to prevent active attacks. If somebody really wants to attack our network or our server, they would probably be able to attack it, but we're going to try to deter them from doing it because of all of the security features that we are going to add into our network. A couple of recommendations from the International Telecommunication Union, ITU. We talked about X200. This is the reference model for OSI. The Open Systems Interconnection model is recommendation X.200. I told you in the previous lecture that X.200 does not include security built into the protocol. However, there are protocols built on top of the OSI model that run in the specific layers that include security. So recommendation X.800 from ITU says below, you see the bullet point there, it defines the general security-related architectural elements which can be applied appropriately in the circumstances for which protection of communication between open systems is required. It establishes, within the framework of the reference model, guidelines and constraints to improve existing recommendations or to develop new recommendations in the context of OSI in order to allow secure communications and thus provide a consistent approach to security in OSI. So this was after the fact. X.800 was created because security was not thought of in the original OSI model, which is recommendation X.200. However, when security started to become a little bit more of an issue, and you can see down at the bottom, the citation I have shows that this was in 1991 is when the X.800 recommendation came into effect. So that's when security really started to be at the forefront of computer and networks. And so they came up with the X.800 recommendation, trying to add security to the OSI model. Here are some of the security services that are embedded in that X.800 paper. I did provide a reference to this on the website. It is a very long recommendation, and my personal suggestion to you is that you peruse through that, but don't bother trying to read the whole thing unless you have insomnia one night. The X800 security services are broken down into 5 different categories. The first one, authentication. Assurance that the communicating entity is who it claims to be. The main way that we go about doing authentication is with a username and password. As long as nobody else has that password, then authentication can be confirmed. That you provide the username and password, and that's kind of our assurance that you really are who you say you are. If your password gets compromised, that means somebody else could act as if they are you. And this is why it's so important for passwords that you try to make them as secure as possible. Utilize numbers and symbols and uppercase letters and lowercase letters, and make it where it's not based on a dictionary word and change it every 3 months, and all of these password security rules that you know and that are so annoying because you have 800 different passwords on every single website that you go to, and when you have to change one of them, now you have to change all of them, and it takes you 3 months before you change all of them, and by the time that you've changed them all, it's time to change them all again. I understand the purpose behind this security, though, is so that other people don't have as much of an ability. It's much less likely that they're going to be able to compromise your authentication. The second bullet there, access control, prevention of unauthorized use of resources. This happens very frequently in local area networks. Maybe there are only certain computers, or maybe only certain users are able to print to certain printers, and they don't want to have unauthorized access to that printer. It could be as easy as that. It could be as much as there is a database server that has all of the all customer information for an entire organization, and you want to make sure that there are only very, very few people in the company that have the ability to access all of the customers' information. So that would be access control. The third one, data confidentiality, protection of data from unauthorized disclosure. Making sure that data doesn't get out. If it's not supposed to be disclosed to certain people, that it's not disclosed to certain people, that certain computers don't have access to data that they shouldn't have access to. One way that we take care of data confidentiality would be with an intranet of an organization. So you would have to have a VPN, a virtual private network. We'll talk about that in one of our lectures in the future. So that if you want to access resources that are within an organization and you are currently outside of it, you can VPN to the network, and then you can have access to it even when you're outside of that local area network. The fourth one, data integrity, assurance that data received is the same as the data sent. This is very important, especially for as much digital communication as we have nowadays, that if I send an email out to the class and I say, hey, the project is going to be due on next Friday instead of next Thursday, that you know that it actually came from me and that it wasn't somebody else sending it. Or data integrity on this one here, that the data actually is correct and that it doesn't say that it's going to be due this Friday instead of next Friday. That's data integrity. We have ways of making sure that the data sent is the same as the data received. We talked about some of these strategies in the networking class. And so there are ways that we can validate both at layer 2 and layer 4 of the OSI model that the data received is the same as the data sent, and if it's not, we can either drop it or we can request for it to be retransmitted. We can also have some error correction codes. We talked about Hamming code and a few other schemes for correcting data if we receive it incorrectly based on how many bits we have that have changed. Maybe take a look back at the lectures from the networking class and read up a little bit on Hamming code and CRC. That would probably help with understanding some of these security services here. The fifth bullet point here, non-repudiation, protection against denial of one of the parties involved in the communication from having participated in the communication. We don't want in digital communication someone to say, I didn't send that, or I never received that. It would be nice if we had a confirmation that it actually was received. We have ways of doing this also. A lot of people didn't want other people to know that they received an email or that they didn't receive an email, or whatever the case may be. This is often a user ability now, so that you can check a box and say, yeah, go ahead and send a read receipt. Oh, they requested a read receipt? Okay, yeah, go ahead and send it. Or you can deny it and say that they didn't receive it. When you're communicating just server to server or client to server, this often is not the case. So you can set that you want to make sure that it was a delivery confirmation on it. And you can at least see that it was delivered, but you might not be able to tell whether or not it was read or whether it was received by your intended recipient. You might just be able to tell, okay, it was received by that email server. Now, I'm not sure if the user actually got it, but I can tell you that at least the email server got it. All right, another categorization for figuring out about different malware is the TEBIT categories. TEBIT is actually a Swedish name, but it's a technical description model for IT weapons. It's meant to function as a common base on which to build new definitions and categorize individual software weapons. One alternative from each category has to be used. Several alternatives from a single category may be used together, and this is useful for figuring out how complex the software weapons are. So you can see all of the different categories that we have here and the different alternatives. So when a piece of malware comes out, this is usually one of the first things that these antivirus companies will do, is they'll come to this table and they'll just start categorizing it, and they'll figure out then how terrible of malware it is and how quickly they need to jump on fixing it, and whether it jumps to the top of the list or whether, oh, well, there's really not that much, it's not really doing that much, or it's not going to be difficult for us to fix this. And then they'll release the updated virus definitions or malware definitions when they get a chance to do it. Okay, the next 3 slides that I have here are going over a couple different pieces of malware, and I want you to I'll read through exactly what they do, explain what the malware is, and then we're going to figure out whether we think it's a Trojan horse, a virus, or a worm. The ILOVEYOU, that was the name of this malware. It was released in 2000 in the Philippines. This piece of malicious code would arrive as an attachment to an email. Some of you may remember this. It was a pretty big one. It made it onto the news. It circled the world numerous times. Upon opening the attachment didn't have an extension, so there's one big improvement that we've made in email attachments in more recent years, maybe in the last decade or so. A copy of the malicious code was sent to everyone that was in that user's Windows address book, and it was sent from the user's, the sender's address. There were some other malicious changes to the user system that were made, so this did require a fix, some virus definitions to be able to fix this. So, is it a Trojan horse, a virus, or a worm? So, if we look back to our definitions of what the 3 of them is, this one would fall into the category of being a virus. It's a self-replicating program that attaches itself to a host program, and it only resides in the infected host computer. So it only resided there, and it would send this attachment off to other computers, and when it got to the other computer, that user would actually have to run that program, run that attachment, and then it attached to that computer. So this would be considered a virus. Our next piece of malware, Alureon. This was released in 2008, so we're getting a little more recent. Alureon allows an attacker to intercept incoming and outgoing internet traffic in order to gather confidential information, such as usernames, passwords, credit card data, etc. It also allowed an attacker to transmit malicious data to the infected computer and modify DNS settings. Oh, that's a bad one. When you can modify DNS settings on a computer, you can really do a lot of really bad things, because that computer might think that it's communicating with Bank of America or Wells Fargo or Alaska USA. However, you're actually going to be sending data to a different server. So you can be transmitting your usernames and passwords because your DNS settings are all messed up, and you're transmitting them to a malicious server instead, and they can get access to usernames and passwords without you even knowing it. And it's going to look like it's still going to your bank account or your credit card or your email. And what they do is they just act as a third party in the middle, a middleman. They transmit that onto the legitimate site, and they get the data back and they transmit it back to you. So it actually looks to you like you are communicating directly with your bank or your credit card or your email. However, what you don't realize is that there was somebody in the middle who's just gotten your username and password, and then they can access this at a different time. So that's really bad whenever DNS settings can be affected by some piece of malware. Microsoft confirmed later on that Alureon was causing the infamous blue screen of death, the BSOD, to occur after releasing a patch for its operating systems. A subsequent patch was then released to fix the vulnerability. Again, this is one of those situations where you don't know whether you should do it or not. Microsoft released the patch, people downloaded the patch, and there was a hole in the patch. And so then Alureon came out, this piece of malware came out, and it took advantage of that hole that was released in Microsoft's patch, and then Microsoft had to release a subsequent patch to fix that vulnerability. All right, do you think this is a Trojan horse, a virus, or a worm? That's right, it's a Trojan horse. It's a program performing unknown and unwanted actions for the user while posing as a legitimate program. You don't realize that there's something else going on in the middle here. What you know is that you're accessing a website and everything seems like it's working just fine, but you don't realize that there's something else going on in the middle. So this would be an example of a Trojan horse. Our third and final one, Morto. Morto was released in summer of 2011. Morto attempts to propagate to additional computers via the remote desktop protocol. Some of you might use RDP. Remote desktop is a very popular protocol now, because you can have a computer that is running at your home or at work, and then from another computer you're able to remote desktop into it and you can control that computer. This is often used for tech support. It's very commonly used for that. It's also used if you have firewalls or other things that are blocked in a certain network, that you can just get to the remote, you can remote desktop to another computer that's in a different network and hopefully get around restrictions there. Once Morto finds a remote desktop accessible system, it attempts to log into the system with a username as administrator and several weak passwords such as admin password, server test, user pass, let me in, etc. It's very important that if you do enable remote desktop on a computer, that you give it a very secure password. If you don't, then Morto just goes around and it finds, okay, this one's got whatever port remote desktop operates on, it's open, let me try this with administrator, and just some random passwords that a lot of people will just set as default because they don't think that anyone's trying to attack them. As soon as Morto gets in through remote desktop, you now have complete access to that computer though. So Morto is able to disable antivirus programs. It's able to do anything on that computer that the user that was able to connect through the remote desktop is able to do. This one could be very dangerous, especially if you have a single user computer on your home computer, because chances are that user has administrator privileges. And so if Morto was able to get in, it could do absolutely anything to your computer, including reformat it, delete everything on the hard drive, disable antivirus programs, install any programs that it wants. Your computer can get into a very, very bad state with Morto. So keep that in mind if you're going to enable a remote desktop on your computers. Would this one be a Trojan horse, a virus, or a worm? The answer to this one is that it is a worm. It's a self-replicating standalone program that replicates over network connections. So it's just going to keep going around computer to computer and find out who has remote desktop open, and then it's going to try different usernames and passwords like administrator with simple passwords to see if it is able to get into those computers. Okay, moving on to a little bit of a special topic for today, security concepts in VANETS, which are vehicular ad hoc networks. Do you think that there are additional security measures that need to be considered for wireless networks mobile ad hoc networks and vehicular ad hoc networks. Why or why not? Hopefully you can see that this is a very, very easy question to answer. There obviously are additional security measures that need to be considered because we've opened it up a little bit. When we're on a wired network, we didn't have to worry so much about the physical security. A lot of the physical security that goes with wired networks runs through walls, it goes through server rooms. When we are finally moving over to the wireless field though, any computers that are within range of that wireless network may be able to see all of the data that we're transmitting. One of the projects for this class may involve you being able to see if you can get access to wireless data when you're sitting in a public Wi-Fi zone. This is not very difficult to do. There's programs out there that allow you to run packet sniffers in promiscuous mode, and you can see all of the data that's being transmitted on a wireless network. If the data is not encrypted, you're going to be able to see usernames and passwords very easily. It's not even something that a computer programmer has to do. You download a program and you just run it in promiscuous mode and start looking at all of the data that you're gathering. Really easy to do. It's something that not many people realize, especially when you're surfing Wi-Fi on public networks at coffee shops or at airports or even at universities if the data is not encrypted. So be careful with that and make sure that you're not going to any secure sites such as banking websites when you're on public Wi-Fi networks. This figure that I have on this slide just shows some of the security concepts and whether how things are signed. We talked about some of these measures last semester. We'll go through a lot more of them this semester in future lectures as well. Okay, a wireless mesh network is just a set of wireless routers that connect to a wired network to provide multi-hop wireless internet connectivity to mesh clients. This is going to become more and more popular with mobile ad hoc networks and vehicular ad hoc networks because vehicles are actually going to act as routers. Some of the newer vehicles that we have now have routers built into them. It's really cool. These routers operate on the cellular network, and you can, if you're within range of the car, you're going to be able to have wireless connectivity to your car's router, and then from the car, it's going to be communicating over the cellular network, and you're going to have internet connectivity from that. So we're going to have a lot of these wireless routers just driving around inside of vehicles, and if maybe one vehicle is not within range of the cellular network, but another vehicle is within range of that one, and that vehicle is within range of the wireless network, we could form a wireless mesh network so that the first vehicle still has access to the internet. And that's what you see down in that diagram down below there, is how they can all access each other. So we have a little bit more security that we need to think about with wireless mesh networks because we're actually transmitting through other routers over which we have absolutely no control. And there's no guarantee that the data is going to get to where we're sending it, and we need to make sure absolutely that if we're sending it through something like that, that the data must be encrypted, because those other routers are going to be able to have access to everything that we are transmitting, and if it's unencrypted, they're going to have access to all of our data, and that's not what we want, especially if it's a router over which we have absolutely no control, and we have no idea whether there's any malicious code running on that router or not. Here are some security attacks that we have in wireless mesh networks. Denial of service attack. Again, we'll talk about this one a little bit more in the future, where we can just flood any centralized resource so that it no longer operates correctly. If we don't like a router or somebody doesn't like ours, they could probably flood us with all kinds of data, and we wouldn't be able to access the internet or the network any longer. An impersonation attack. Without proper authentication of the parties, compromised nodes may join the network, send false routing information masquerading as a trusted node. We have to really be careful that if there's malicious nodes within our wireless mesh network, we need to know this so that we can hopefully try to prohibit access to those nodes, or at least alert them or alert the user that maybe there's something wrong that they need to fix. And then there are a lot of different routing attacks. The paper that you see that I've referenced down there at the bottom by Redwan and Kim, there are a lot of different routing attacks. Read through the paper. It goes through detail of all of those. The routing table overflow attack, the wormhole attack, the black hole and the sinkhole attack, the location disclosure attack. There's one more that it goes through. It was described in a little bit more detail in another paper, so I referenced this one here. It's the Byzantine general problem. It was referenced originally in 1982 by Lamport. This is a very, very popular paper. Of all of the papers that I've posted for today's lecture, this is by far the one that I think is the most important. So please make sure that you spend time reading this paper and understanding exactly what the Byzantine general problem is. An overview of it is assume that we have N generals, some of which are traitors. And each general is going to be sent a message from all of the other generals, and we need to know whether we should attack or whether we should retreat. And what we're going to do is we're going to take a majority of the messages, and if the majority of the messages say attack, then we are going to go ahead and attack. And if the majority say retreat, we're going to retreat. The question now, how many generals can be traitors for us to still make the right decision? Because we don't want the traitors to all tell us to attack when they're not going to, and then we're going to be slaughtered. So the paper goes through a nice long analysis. It's not very difficult. The math in this paper is not very difficult, so please take the time to go through it. And the conclusion is that we need to have at least 2/3 of the nodes be loyal. If more than two, or if fewer than 2/3 of the nodes are disloyal, then chaos can occur, and we could be attacking when we should be retreating, or vice versa. Let me pull up the website here. So if you go to the lectures page on the course website, you will see here the papers for today. Here's the one that I just referenced. That is the one that I think is the most important, the Byzantine General one, written by Lamport here in 1982. So grab that PDF right there and read that. Make sure you take a look at these other papers that I have posted for today also. The slides are posted here. The lectures will be posted over here on the right-hand side. If you have any questions, shoot me an email, and I will see you all in our next lecture.